Assalamualaikum and very good day. My name is Emilia Elyasa and the metric number is 19648. I'm from the Department of Chemical and Environmental Engineering, and today I would like to present my final year project with the topic of investigations of hydrodeoxygenation process of oleochemical waste oil for paraffin production using non-noble methods. Generally, this research project is to assess the characterizations of catalysts, a type of somatic catalyst provide the hydrodeoxygenation reaction, which is HDO, and examines the reaction pathway for the deoxygenation process, which is DO, on the three non-aromatic catalysts that have been chosen, which is the nickel alumina, cobalt alumina, and iron aluminum oxide. For introduction, the oleochemical waste oil is a waste from the oleochemical industry. For example, like fatty alcohol productions from palm oil fatty acid. This oil is being reused as an energy and intermediate chemical due to the high concentrations of alcohol derivatives inside it. To produce an energy, the oil needs to undergo the deoxygenation process, which is the removal of oxygen. There are several pathways for this process, and based on this graph, the main pathway that has been identified from our previous study is basically the hydrogenation, which is also known as HDO, and the hydrogenation, decarbonation, and decarboxylation, which is DCO. From this pathway, we can see that HDO only producing water as a byproduct, meanwhile DCO producing carbon monoxide and carbon dioxide. These gases contribute to environmental issue which we want to reduce from the industry. So the optimizations of HDO pathway needs to be conducted. The type of catalyst used in the reactions has the biggest impact on this pathway. Nonetheless, there is a lack of literature on this parameter for oleochemical waste oil. Thus, this study used different types of catalysts to improve the HDO pathway in the DO reaction for oleochemical waste oil. Next is the methodology. The experiment started with the preparations of feed and the catalyst. The feed was prepared by dilution with the hydrant, which is 1% dilution. At the same time, the catalyst was prepared by in-situ wetness separation method to get the fresh nickel, alumina, and cobalt alumina catalyst. Then the prepared catalyst and feed was used in the HDO process using a feed fed reactor at a temperature of 260 and 200 degrees C with a pressure of 20 bar. The product was undergoing VCMS for qualitative analysis and VCFID for quantitative analysis. Meanwhile, the catalyst was characterized using XRD and BC analysis. What is the result? The result, the EP analysis shows that the surface area of raw alumina, nickel, and cobalt after drying, nickel and cobalt after calcining, after reduced with hydrogen, and after being used. The main point from this result is basically the surface area of nickel alumina is greater than cobalt alumina. This also outside the conversions of the feed, where the nickel has a higher conversion than the cobalt. However, this conversion is not outside the selectivity of the lithium for each of the catalysts. Next, the XRD. The pattern of the catalyst reveals that all samples were well crystalline during the calculations at 500 degrees C for 5 hours for reduction and 200 degrees C for 5 hours for reduction. Calculation. This can be seen from the graph where for reduced and calcined nickel alumina, the peak for a nickel oxide and nickel alumina oxide and also alumina oxide generated. So that's for the cobalt. So thus we can conclude that our catalyst is successfully prepared using a wetness separation method as this compound present in the catalyst. Then we proceed to the next one, that is the oxide catalyst on HDO process. For conversions of 1-decanol, as mentioned earlier, nickel alumina oxide has a higher conversion than cobalt, and iron aluminum oxide has the highest conversion compared to nickel and cobalt. This is because iron aluminum oxide has the highest surface area than nickel. When the surface area is higher, it provides greater exposure of reactant gases to the metal active site. So it causes the conversion to be higher. Next is the production rate of the lithium. Based on the graph, the cobalt alumina has the highest production rate of the lithium, followed by iron aluminum oxide and nickel. This has a correlation with the selectivity of the catalyst on the metal catalyst site. Now we proceed with the selectivity of the lithium. From the graph, we can see that the cobalt has the highest selectivity at the end of the reaction as it achieves equilibrium. Cobalt has the highest selectivity, causes the high production rate even with the lowest conversion. This is due to the an absorption structure of cobalt, which is able to reduce the activation energy for the lithium production better than other catalysts. It also because the active site on the metal catalyst for cobalt is capable of capturing oxygenated compounds without carbon from the reaction in the presence of hydrogen, so resulting in the highest selectivity of the lithium. On the other hand, nickel aluminum oxide and iron aluminum oxide, so the structure active metal sites have active metal sites that are not suitable for formation for lithium, but rather altering with lower carbon numbers, such as anthracis and nonene. This is the reason of the lower the lithium production rate for nickel and iron aluminum oxide catalysts compared to cobalt. Then I will proceed to the reaction pathway. Basically, from the year of the product, we can determine the reaction pathway shown in figure 1. The lithium yields HDO will favor on the lithium field and DCO will favor on lithium field. So based on this graph, the lithium field graph, it reveals that cobalt has the dominance in the HDO pathway. But for lithium field graph, it shows that the nickel aluminum oxide is dominant in DCO because the yield for the lithium and also the lithium is highest. In short, it is believed that the applications of cobalt can increase the highest conversion reaction rate toward the lithium future paraffin production. So for future recommendations, so the next study can include analysis of gaseous sample from the product to determine the detailed pathway of the reaction. That is all from me, and thank you.